connected virtually, nationally, and internationally. On behalf of IASTA, I warmly welcome Professor S. Ramachandran from the Space and Atmospheric Science Division, Physical Research Laboratory, Ahmedabad, and esteemed participants to the 23rd IASTA Monthly Lecture Series. I am Dr. Amit Kumar, a member of Executive Committee of IASTA Association. IASTA, since its establishment, has consistently upheld its mission to promote, encourage, and advancement of the aerosol science and technology and their multi-faced application with the Indian context. A vital aspect of our mandate is to provide a robust platform for the scholarly discussion and pioneer development in the aerosol science and technology field. To fulfill this mandate, we diligently curate diverse outreach program and activity, including prestigious IASTA National Conference hosted annually across various places within the country. Under the guidance of Dr. S.N. Tripathi, the esteemed president of IASTA, our EC committee remain fully committed to augmenting our role and fostering support for the spectrum of initiative catering to the research scholar, technocrats, and wider public at large. An integral setup to this direction in initiating series of monthly online lecture delivered by eminent aerosol scientists and engineers across the globe reputed. At this juncture, I am privileged to inform you that IASTA is holding this year 14th Asian Aerosol Conference 2025, which will be held in a vibrant city of Mumbai from 1st December to 4 December 2025. Last date is approaching for abstract submission. It is in up to 1st August 2025. I now extend my request to Dr. Sunita Kedia to introduce our distinguished speaker for today's lecture. Dr. Kedia.
Thank you, Dr. Amit. So, good evening, everyone. It's my great pleasure and honor to introduce today's distinguished speaker, Professor S. Ramachandran, who is also my PhD guide. Dr. Ramachandran is a well-recognized researcher in the field of atmospheric aerosols and their impacts. He is a senior professor at the Physical Research Laboratory, Ahmedabad. He works extensively on the measurements of aerosol properties using state-of-the-art techniques, as well as modeling their impact on radiation budget, atmospheric temperature, and climate using radiative transfer, general circulation, and global climate models. He is an author of the 2007 Climate Science Assessment of the IPCC, which shared the 2007 Nobel Peace Prize. He is a reviewer and an author of the WMO Scientific Assessment of Ozone Depletion. He was a member of the International Radiation Commission from 2001 to 2008. He was a visiting research staff member in the Atmospheric and Oceanic Sciences Program, NOAA GFTL, at Princeton University during 1997 and 2004. He was a senior fellow at NASA Ames Research Center, California during 2008 and 2011 under the NASA postdoctoral program. He was a senior fellow at the Research Institute for Sustainability at the Helmholtz Center, Potsdam, Germany in 2019. Dr. Ramachandran received the prestigious INSA Young Scientist Award in 1997, the Global Science System for Analysis, Research and Training START Young Scientist Award in 2002, the START Visiting Scientist Award in 2004, and the NASA Group Achievement Award in 2009. With a research career spanning over 35 years, Dr. Ramachandran has made significant contribution to the atmospheric aerosol research community and has published about 130 research papers on aerosol, radiative effects, and climate in referred international journals. He is amongst the world's top 2% scientists as per the list published by Stanford University. He is an associate editor of the Frontier in Environmental Science journal, and he has authored a book entitled Atmospheric Aerosols, Characteristics and Radiative Effects, published by CRC Press, Taylor and Francis Group, USA, which is an exclusive textbook that comprises many new information on a wide variety of fields related to atmospheric aerosols in the troposphere and stratosphere. Beyond research, Dr. Ramachandran is a dedicated mentor who has supported and guided many students, including me, with a deep commitment and strong focus. Today, Dr. Ramachandran will be speaking on aerosols, radiative effects, and climate observations and modeling challenges. With this brief introduction, I now welcome Dr. Ramachandran to deliver his talk.
Is the slide visible?
Yes.
Okay. At the outset, I'd like to thank IASTA and Professor Rastogi for the invitation to give this monthly lecture in this IASTA monthly lecture series. I am truly overwhelmed by the fact that I am being joined by, for this presentation, I am joined by my students, postdocs, and my mentors, including Dr. Devara. And it's definitely a pleasant surprise for me, both Neeraj and Sumita. I never expected that she will be introducing me. So that's been a overwhelming experience. And also that one of the objectives of the lecture is that we keep hearing about aerosols, radiative effects, and climate. And then we also see several results that have come up in the last few decades. But the focus of today's presentation is what are the challenges that we face in terms of observations and models, and where is it that we lack. So I will begin with the introduction and then go into the details of the aerosol characteristics that we are properties that we measure and we model, and what are the difficulties or the uncertainties, and then how these aerosols impact the radiative budget, and finally, how we can attribute this to these aerosols to climate. So aerosols, as most of us know, that these are solid or liquid particles suspended in air. They constitute a major element in the atmospheric and climate sciences. They are produced by both sources which are natural, meaning from oceans, deserts, terrestrial biota, material of plant origin, smoke from burning of plant biota, and anthropogenic particle emissions, which include terrestrial ejecta as well. Just a second.
Ramachandran? He said just a second, right?
Yeah, I'm back.
Okay.
There was a disturbance in the adjoining room.
Okay.
So I had to go and stop the work.
Okay.
So the secondary or the indirect sources is the major source of particles for less than 1 micrometer in radius, which is the gas to particle conversion. which conversion mechanism. They illustrated size spectrum and the shape of the particle.
Slide has gone. Professor Ramachandran, your slides are not visible. It is unshared. Hello?
Yeah.
Your slides are not now.
Is it okay now?
No, it is not visible at all. I think it is unshared now.
Okay, wait a minute.
Actually, in our place, it is showing. In my PC, it is showing slide.
Yes, visible.
In my PC also it is showing.
Yeah, I'm able to see.
So is it me only? I don't know.
Yeah,
Yeah, it is showing.
Then
Please go ahead.
okay. So the size spectrum and the shape of aerosols that we determined is based on the formation mechanism, the source from which they are produced, while the production source determines the chemical composition of these particles that are present in the atmosphere. When it comes, these composition and the size range, in terms of the source strength, each of these component in terms of the mass and a number of difference in the atmosphere as a function of size. As in any other field of science, in terms of basic, because of their role that they play in radiative transfer and climate, we need to know investigate and understand several of these characteristics. The primary sources of particles include starting from very small hot vapor that can condense on the primary particles like sulfate, nitrate, etc., which then can coagulate and go to the accumulation size range, which is the particles which are of in the size range of 0.1 to 1 micrometer. And these particles can also grow in terms through condensational growth and then can become bigger. While in the coarse size range, particles that are greater than 1 micrometer, the natural aerosols that are emitted from windblown dust, emissions, sea spray, volcanoes, plant particles, these form the coarse mode or coarse size range because these are typically particles that are greater than 1 micrometer. Now, how do they manifest? These manifest in terms of the very famous pictures that we know. This is the Indo-Gangetic Plain. We are very familiar with this scenario every winter. And then this is the Los Angeles smog that was experienced a few years ago. And then this is Delhi during 2018. Now, when we classify these aerosols into different types, these are sulfate, nitrate, sea salt, mineral dust, black carbon, organic, or brown carbon. When we differentiate this in terms of the natural versus the anthropogenic sources, the natural aerosol sources, namely the sea salt and the dust, are more scattering when compared to black carbon or any other species that is emitted from the anthropogenic sources. Now, these aerosols can induce or can be manifest at local, regional, and continental scales. And this is what are the illustrative images that we saw. So when we remove these particles, just as it happened in 2020, we can see that the effect on air quality as well as the visibility. It is the same scene that you are seeing on the left, above in 2018 and below in 2020. Thus, indicating or suggesting the impact of aerosols on air quality and climate. The time that is spent by these particles in the atmosphere is a function of size and the height at which these are located. So typically, when the particles are of smaller size, the process such as coagulation and condensation and gas to particle conversion happens. and typically they spend about a few hours to about half a day in the atmosphere, and then they graduate to the next size range, which then condense and coagulate to form bigger particles, and then through mechanical disintegration, sedimentation, and wet removal, they can get settled out of the atmosphere. This typically there are about 10,000 particles near surface, which gradually will decline based on the formation and the settling process that are at work. They become 5,000 in about like 5 kilometers or so, and then above it's about 500, and then when you go to the free troposphere and above in the stratosphere, etc., you'll find typically there is 2 kilometers, and then when you go to free troposphere, it's about a week. Gravitation settling and all are weaker than near the surface. Then once it crosses the troposphere and then go to stratosphere, their lifetime is extended to about 1 or 2 years. And they typically take about 2 years from stratosphere to come to troposphere and then to the surface, and where they get settled through either wet removal or gravitational sedimentation. They also can get transported across to other locations or regions through diffusion, some of which process that we'll see as the lecture proceeds. When we characterize the aerosols over the environment, for example, let us try to contrast the urban versus any other region. Typically in urban regions, because of this fossil fuel and biomass emissions, most of the particles that we see are from combustion, mainly anthropogenic sources. These are essentially gas to particle conversion mechanism for those particles. And typically the fine mode particles that are smaller than 1 micrometer are more abundant than particles that are greater than 1 micrometer. And urban emissions are dominated by Asian context, especially black carbon, water soluble, which includes sulfate, nitrates, etc., and also insoluble aerosols. When we compare and contrast this urban with maritime or background or remote continental location, the major striking difference that comes the size of the particles and the number of particles that are smaller than 1 micrometer. In the fine mode, particles that are smaller than 1 micrometer, the number of particles in the urban scenario is at least 10 to 100,000 times. There is number is more, 10,000 to 100,000 difference in terms of the number density that we can see. And the particles are of smaller size as compared to the particles that are in the maritime or a background scenario. And the other major difference when it comes to the particles of larger size, we see that in the maritime or a background condition, the number of particles in the Querce mode is higher than particles in the fine mode. And while in urban, for example, the fine mode particle density is much higher as compared to Querce. This was the distribution that we saw in different environments. But when it comes to the aerosol and its impact on climate, we rely on 3 aerosol properties, namely the aerosol optical depth, single scattering albedo, and the asymmetry parameter. As was mentioned in the beginning, this lecture will concentrate or focus on aerosols, their radiative effects on the climate. We will take one by one each of these parameters, and then we'll try to focus on the difficulties and the challenges. Aerosol optical depth is nothing but the scattering and the absorption due to the particles that are present in different size ranges as a function of the altitude. Or in other words, it is the amount of radiation that is sent back, scattered or absorbed by the aerosols present in the atmosphere before they reach the surface. And the effects on scattering, effects due to scattering and absorption, they differ. And we know that sulfate and sea salt are scattering type aerosol species, whereas black carbon, organic carbon, and dust absorb the radiation that they interact with. So in simple terms, it is the integral of the number of particles at each size, at each height, and then their scattering and absorption as a function of the radius, and then you integrate them all up to about 40 kilometers, up to which the aerosols are present. We see significant seasonal and regional differences in terms of in aerosol optical depth, as is illustrated in this figure. The urban industrialized regions have higher aerosol optical depths, and regions such as Africa, South America, etc., due to dust and biomass burning, as a function of the season, the content vary, which are very clearly captured in this figure. Next comes the ratio of the scattering to the total extinction, which we call as a single scattering albedo. One, if the single scattering albedo is 1, then it means a pure scatterer, while anything less than 1 is an absorber. Among the species, for example, sea salt and sulfate are the scatterers, while black carbon is the single largest absorber of both solar and the long wave radiation. Organic carbon and dust, they are scatterers, but their single scattering albedo is closer to 1 as compared to sea salt and sulfate. Similar to the aerosol optical depth, this ratio of scattering to the aerosol optical depth also shows significant seasonal and regional variations depending on the sources. For example, whether urban emissions, which are more higher in terms of the fossil fuel, or dust or biomass burning emissions, they dominate the atmosphere, or sea salt dominates the atmosphere, then the ratio will vary as a function of time and space. So we see that the single scattering albedo is kind of less than 0.9 in regions where there are more absorbing aerosols present. Now this is in quite contrast to the aerosol optical depth. There may be regions where the optical depth is lower, but the single scattering albedo could also be lower or higher. More of these features, their distinction will be analyzed in the later part of the lecture. The third most important parameter is the asymmetry parameter. This is nothing but this signifies the angular distribution of the scattering that takes place when the aerosols interact with the incoming electron radiation. When it is the scattering is isotropic, then the asymmetry parameter in this case increases, just as like for example, keeping aerosols, so the asymmetry parameter is lower as compared to sea salt or sulfate, the asymmetry parameter is higher. Now, let's try to where they are in the environment. They vary as a function of the environment where they are. They will vary as a function of sources. Meteorological conditions, for example, such as relativity, winds, the planetary boundary layer or the atmospheric boundary layer height, rainfall, they also determine and influence the aerosol characteristics, both the AOD, single scattering albedo, and the asymmetry parameter. Then these particles that are produced over a particular region can get transported in terms of to higher altitudes through convection and also through diffusion to other latitudes. And this where the diffusion and the dynamics play an important role in determining the particles that are present in the atmosphere at one location. And finally, they also depend on season. For example, when during we are all familiar with during pre-monsoon over the Indian Asian scale region, we have a large amount or influence of dust in the atmosphere as compared to the other seasons. If you look at the numbers, aerosol, optical depth, single scattering albedo, asymmetry parameter, for example, in the urban scenario, the aerosol optical depth is 0.6 and the single scattering albedo is about 0.8, while other regions, the aerosol optical depth is lower than 0.4, but the single scattering albedo is much higher than 0.8. The asymmetry parameter for all these different types of the aerosol types that are present in the atmosphere, ranging from continental to marine, including desert, they are on an average above 0.6 and below 0.8. We talked about the meteorological conditions that would either favor or worsen the pollution scenario. For example, scenarios include when the wind speeds are high, the relativity is low, when the hygroscopic growth of these particles, like for example, sulfate of sea salt is restricted, then and the boundary layer is higher, then we also have a rainfall, then wet deposition, which will favor early dispersion of pollutants, which means that the AOD will be lower, the aerosol content being removed from the atmosphere will be lower, and also the single scattering albedo, because this is now dominated by particles that are scattering types. Then the single scattering albedo will be higher. In contrast, when the wind speeds are lower, the relativity is higher, and the atmospheric boundary layer height is lower and less rainfall. Smoggy, hazy conditions, they worsen the pollution scenario. It will increase the aerosol optical depth, but at the same time, lower the single scattering albedo. The impact of this on radiation and climate will be seen towards the end of the lecture. The radiative forcing, the common measure that we use to determine the climate impact of the species that are present in the atmosphere, is a measure of how the energy balance between the incoming solar radiation and the outgoing infrared radiation in the Earth atmosphere system is influenced and factors that affect climate or altered, including aerosols. This radiative balance controls the Earth's surface temperature. In contrast to the greenhouse gases, the radiative effect and the climate effect due to aerosols differ based on whether the particles are scattering type or the absorbing type. In terms of scattering aerosols, because the radiation that it interacts gets scattered back by these aerosols, so less radiation will reach the surface. It will be localized cooling, and then the atmospheric circulation will mix, and the mixing process will spread the cooling both regionally and vertically. Between the scattering and the absorbing aerosols, because one will scatter, the other will absorb. At the surface, the effects are the same, which is one of cooling, because both these particles will prevent the radiation that is reaching the Earth's surface, which is a loss, and hence they produce cooling. When it comes to absorbing aerosols, initially there will be localized cooling, but the altitudes above the surface where these particles are present, they will warm the atmosphere. The same circulation and the mixing process will redistribute the warming, as we saw when cooling is spread both regionally and vertically, and the net effect will be one of warming. However, we look at the proportion of cooling to warming, the cooling will dominate, and hence these aerosols have offset the greenhouse gas warming of the Earth atmosphere system. The other important effect of aerosols, which we call as the indirect radiating effect, is that these particles, depending on where they are, meaning the environment, they can modify the optical properties and lifetimes of clouds, which we call as cloud albedo and the lifetime effect, wherein when we go from a cleaner to a polluted environment, which consists of more aerosol particles, as is shown in this figure as compared to a cleaner environment, shown by the red dots here, there will be more reflection, higher albedo, and smaller cloud particles and less precipitation. When in a cleaner atmosphere, for example, you see these red dots, which are aerosols, are much less when compared to the cloud droplets. And not only that, the cloud droplets size also is higher than here, as in polluted conditions, leading more precipitation to occur. When it comes to semi-direct effect, when these aerosols happen to be the absorbing aerosols, such as black carbon, for example, this heating, because they absorb the radiation, that can evaporate the cloud droplets, and the cloud can shrink, leading to due to the absorption and can have a semi-direct effect of both radiative and the indirect influence on the cloud properties. Climate is determined by a number of complex, connected physical and chemical and biological processes occurring in the atmosphere, land, and ocean. The radiative properties of the atmosphere, a major controlling factor of the Earth's climate, are strongly affected by the biophysical state of the Earth's system surface and by the atmospheric abundance of variety of trace gases and constituents, including the long-lived greenhouse gases, ozone, aerosols, etc. Now, the composition of the atmosphere is determined by the natural and anthropogenic emission of these gases, aerosols, transport that occurs at a variety of scales, and their chemical and microphysical transformation. To put in a nutshell, any variation in any of them in the constituents that make up the climate, that can lead to a climate change. Climate is a long-term or 30 years average of weather. A climate change we define as a change in state of climate that can be determined by changes from the mean and or the variability of any of these constituents or the properties of the Earth atmosphere system. As was mentioned earlier when we were discussing the aerosol radiative effects, this recent IPCC report that came out in 2021, the observed warming is driven by emissions from human activities, with the greenhouse gas warming partly masked by the aerosol cooling. That is also shown here in terms of the radiative effect, namely the radiative forcing, the difference between 1750 2019, and we can see that the aerosols contribute the largest uncertainty climate. The major factor that gives rise to this uncertainty is the magnitudes and the trends of aerosol properties, the three of them that we discussed before, and more especially in particular the aerosol absorption. Why and how, we will see in a few minutes from now, is a major source of uncertainty. Translating this forcing into the climate impact, the contributions to warming, global warming that we see, for example, then the greenhouse gas warming we see here as compared to the observed one, and then the net balance, we can see that there is a large uncertainty. The temperature attribution effects among the species that is it observed warming natural process as seen before, or is it due to human activities? So that is answered in this view graph. When we input the two naturally occurring or natural process variations in the climate and simulate climate effect due to them, which is solar radiation, the variation in solar radiation on the volcanic eruption, which inject megatons of sulfur dioxide particles into the atmosphere and then produce a cooling of the Earth's atmosphere, we see that they are not able to simulate the observed warming, which is in black, shown in black here. So when we put the human and the human causes, namely increases in CO2, aerosols, ozone, etc., then we see that the brown color line matches with the observed, and hence this observed warming is driven by emissions from human activities is very clear from this scenario. Of course, I don't need to tell this audience that air pollution is the fourth leading risk factor for early death worldwide, surpassing high blood pressure, tobacco use, and poor diet. Typically, the levels that particulate matter less than 2.5 and less than 10 micrometer are much higher than the levels that are prescribed that we are breathing. This is just for the completion of connecting air pollution or aerosols to human health. Now, let us come back to the issue of connecting aerosols to radiation and to climate. So let us first begin with how the aerosol optical depth observations from the satellite and how the model simulations look like, and then we will go take it through. So what we are looking at is the results, the aerosol optical annual means for about 15-year period from two models and the satellites, namely the ozone monitoring instrument MOBIS and MISER, and the models are MERA2 and CAMS, which the audience are familiar with, and also the coupled model intercomparison project phase 6, CMIP6 model mean AOD is also shown as a reference. We see that the optical depth, the features, the range are very well captured by satellites and the models in comparison to also with respect to the CMIP6 AOD. Now, this is a very, very broad picture. Now, when we look at more closely, as we will see in the next few slides, that the differences will start dropping. Then let us move on to the single scattering albedo. Again, the sequence is the same. These are from the two models, the three satellites, and compared it with the CMIP6 model in single scattering albedo. Compared to the, please note that compared to the aerosol optical depth, the scale, single scattering albedo scale is, or the range is quite narrow. And we also start seeing differences in the single scattering albedo among the models and among the satellites as well, as compared to uniform distribution of aerosol optical depth in both these scenarios, both these conditions, namely from model, satellites, and also CMIP6. Now, as we saw, there are different sources, different regions produce or abundant in different sources. Then these aerosols also get transported across as a function of height, as a function of the diffusion, etc., leading to variations in the aerosol optical. Now, we saw initially that the major species that are there in the atmosphere that we can call as sulfate, dust, organic carbon, sea salt, and black carbon. And on the left, you see is a general description of the contribution of different types to the total optical depth that we see. This is shown from MERA2, but take it from me, the scenario is more or less the same as we do it in CAMS or even in CMIP6. Typically, the aerosol optical depth is dominated by sulfate, organic carbon, followed by dust during a particular season or a particular region, and sea salt AOD is dominant only over the oceanic surfaces, and also when the wind speeds are higher than 4 to 5 meters per second during a particular season. As compared to these four species, the contribution of black carbon to total AOD in the atmosphere is significantly lower, at least a factor of 3, as we can see from the scales. And these are also concentrated in the industrialized regions and where biomass burning dominates, as we can see the intensity of the black carbon contribution. And this is a familiar figure that we saw in the previous 2 slides. The optical depth is higher over regions where there is a large urban emission and also dust and biomass burning contributing to higher. Now, first, let us begin with the observations. These are results from the studies that we conducted in the last few years. We used the aerosol characteristics from the aerosol robotic network. I'm sure the audience knows what is aerosol robotic network. In short, it is the AeroNet, the sun sky radiometers that are several places across the globe and measures both direct and the scattered radiation in different wavelength regimes. In this study, we used the AeroNet level 2 version 3 all points data because one of the objectives is to address the challenges that from the observations and the model simulation side. So we needed very high resolution data that is available from the observations, and hence we used all points data. These are not available during the 5-year period between 2015 to 2019, because we saw that this was the time when maximum number of available observational sites, more than 250 aeronet sites, the data was available, and we avoided the data during 2020 and 2021. As the audience know that during the COVID-19 lockdown conditions, they changed or modified the aerosol characteristics, including the aerosol optical depth, where a large reduction across the globe was seen, anywhere between 20 to 40%, including the changes in single scattering algorithm. When we set out with this objective, looking at the number of years, we also put several stricter criteria. Typically, I'm sure you are familiar with observations or studies wherein annual data is used or a particular seasonal data is used, and then inferences are drawn. But in this study, we enforced more stricter criteria for selection of observation sites, which means these are the following, which are all column aerosol properties should be available, namely aerosol optical depth, the angstrom exponent, single scattering albedo, size distribution, radiative forcing, etc. Must cover all the 4 seasons in a year, and the data should be available for at least 9 months, because one of the other objectives was that whether the intra-seasonal differences or the season to season differences, are they prominent, are they worth looking at, or is it different over a particular region while it is prominent in the other region, or it doesn't change anywhere in other regions. This was also one of the objectives of the study. So this is the distribution of the aeronaut sites that we analyzed from during 2015 to 2019, the results of which you are going to see starting from the next slide. First, I will begin with the aerosol optical depth, then move on to single scattering albedo, and finally to aerosol radiative forcing. So on the left is the aerosol optical depth, drawn again as a function of the season in all the locations that we saw in the previous figure, namely the annual, winter, spring, summer, and autumn. Compared it with the MODIS AOD just for familiarity. And at the outset, we see very clearly that there are seasonal and regional differences. And AOD is highest over Asia, South Asia being the highest, 0.61. These are annual mean figures. These are from Aeronet once again. Southeast 0.38, East 0.34, and Central Asia. Except Africa, rest of the world, both the magnitude and the space-time variability in the aerosol optical depth are at least 2 to 4 times lower than Asia. And AOD is lowest over Australia. And it's also very clear that the MODIS AOD is overestimating, or MODIS AOD is higher than Aeronet AOD. On the right, we are seeing the bias, which is the MODIS AOD minus the Aeronet AOD. You can very clearly see that MODIS is overestimating AOD across almost all the regions of the globe. And the biases are on the order of about 40 to 50%, as we can see from the scale, which can be from -0.2 to 0.2, while the scale here is above 0.8. Now, as was mentioned earlier, one of the challenges was how do these observations compare with models. Now, the Global Climate Observing System sets out a very strict and a generalized observational requirement for the data, the required data that is demanded by the climate modeling community. For example, for AOD, the requirement is that the accuracy of AOD should be better than 10% or 0.03 of the AOD. So that means that translates into maximum 0.04 or 10% of AOD. And for SSA, it translates to plus or minus 0.03. Now, we have calculated what is called as the G-cos fraction, and is shown it here. This corresponds to fraction of model and or satellite. In this case, is a satellite AOD or SSA, whose differences with respect to the Aeronet AOD or SSA lie inside the G-cos requirement envelope, which is 0.04 or 10% of AOD. Now let us look at the figure on the top, and then we move on to the probability of the spectral distribution of different AOD and the total. So we see that the GCOS fraction is higher over, for example, North America and Europe as compared to what we see over the Asian region. And the mean bias error is also lower for the North America and the Europe regions, where it is much higher in terms of negative magnitude of the Asian region and a few other regions. The correlation coefficient varies between group to band. However, there are reasons for this agreement, depending on whether the high AOD is simulated better or the lower AOD is simulated. Now, let us look at the figures below, where this GCOS fraction is now plotted for total optical depth as well as for three conditions of AOD, namely AOD less than 0.25, AODs between 0.25 to 0.75, and high AODs, as we see, as we are familiar with the Asian region, greater than 0.7. Now let us concentrate on the total AODs, which are in black here. If you look at the probability distribution, the GCOS fraction, which is shown here as GL, is much lower for the Asian region. It's a little higher over Central Asia, but contrast this with, let us say, North America and Europe, which is more than 65%. North Africa also, it is lower because of the high AODs during a particular season. Now, this is from the MERA2 model AOD, and the scenario is almost the same for the other model which we talked about earlier, namely CAMS. So if you look at very closely the optical depths that are generated more than 0.75, the GCOS fraction still reduces further. So this is a scenario or the impact that over the region where the aerosol optical depth is high, the GCOS fraction is significantly lower than we get for the other conditions or other scenarios. Now let us look at the next parameter, which is the single scattering albedo. Same aeronet plotted here. As was mentioned earlier, please note that the ranges of AOD and the single scattering albedo are quite different. Single scattering albedo range varies between 0.8 to 1, whereas the AOD varies between 0 to 0.2. Keep that in mind while we discuss this. So when we discuss the scattering versus the absorbing nature of particles, namely the single scattering albedo, we do classify them as more absorbing when the single scattering albedo is lower than 9, moderately absorbing when the single scattering albedo is between 0.9 to 0.95, and less absorbing or more scattering when the single scattering albedo is more than 0.95. Now, SSA at the outset is very clear, is lower because these are more absorbing over Asian region. As clearly seen here, the values are less than 0.9. And North America and Europe, these are greater than 0.9 and sometimes greater than 0.95, indicating that these are more scattering type of particles that are dominating, which we also saw in the species AODs. The aerosol composition, the ratio of scattering to extinction also over North America and Europe does not show significant seasonal variation. Whereas over Africa and South America, large significant changes in the seasonal variations are visible because of the presence of dust and biomass. In contrast to the AOD, the OMI retrieves a single scattering albedo. It is more absorbed. So the OMI SSA is lower than aeronet SSA. And the biases, if you look at it, for example, it is on the order of about 0.05, both in positive and negative scales. And as in terms of the magnitude of the bias in SSA is also lower. It's about 4 times lower than what we saw in the AOD. Let us do the same exercise for looking at the probability from MERA2 and look at the GCOS fraction, which is the stricter requirement for the observations to be put in the climate model, and see how they vary with satellite and the other model requirements. Then we once again see that the GCOS fraction, for example, varies between south, east versus North America and South America. The values in contrast to AOD, the GCAS fraction for single scattering albedo is higher over Asia because the values are higher. Single scattering albedo is lower, similar to what we see here when OMI is reproducing. Because OMI retrieves lower SSA, and Aeronet over the Asian region also we retrieve lower SSA values. Now here, for example, North America, where the scattering aerosols dominate, the GCAS fraction decreases. And here, these differences are also more evident when we classify them in terms of aerosols which are more scattering, moderately absorbing, and more absorbed. Now let us move on to the impact of this. Changes in the AOD, changes in the single scattering albedo, how they contribute to the aerosol radiative forcing. On the left is the aerosol radiative forcing at the surface with varying between 0 to minus 18 watt per meter square. This is the radiation that is blocked or prevented by the aerosols from reaching the Earth's surface. The negativity is the more cooling effect that we observe the surface as we saw before. Compare this with the clouds and the Earth's radiant energy system, Cirrus satellite fluxes, which uses MODIS AOD to derive the aerosol radiative forcing. We see that the significant seasonal and regional differences that we saw in AOD and SSA are visible in the aerosol radiative forcing as well. And the aerosol radiative forcing is significantly high over Asia, consistent with the high AOD and the low SSA we saw. The values are lower over North America and Europe. Again, we know the reasons why they are. The seasonal variations over Africa and South America are brought out because of variations in dust and biomass. The air that is produced by cirrus is greater than Aeronet. As we can see that the values are more negative. Look at the numbers that we are now looking at. We are examining. The forcing went all the way up to minus 80 watt per meter square. The biases can be on the order of about 2.5 to 3 times, depending on the region and whether they are under or overestimated. Magnitudes are very, very close in terms of the values, also the biases. Let us do the same exercise as we did for aerosol optical difference in this video. We see once again that the mean bias error that is plotted here on the RMSE, the root mean square error is actually much significantly higher over South Asia and Asia in general when compared to North America and Europe. Once again, highlighting that the global aerosol hotspot that Asia is, and also the kind of aerosols that we encounter, both natural and the anthropogenic aerosols coexist, and then they contribute to high AOD aerosol content and also lower single scattering albedo. Now, let us move on to the aerosols and radiative effects that are obtained from the CMIP6 simulations. This is the coupled model intercomparison project phase 6 simulations of the results obtained. What we are seeing is the model mean from 6 of the simulations that were conducted as a part of CMIP6. And then this is the AOD on the left, single scattering albedo, and then the aerosol radiative forcing at the top, surface, and in the atmosphere, which is the difference between the two. On the plot, on the regional map that you are seeing, we have also plotted the values of Aeronet that we saw before in the previous figures, which are shown here as circles. These differences are highlighted in the next few slides. What we can clearly see the large difference between the model simulated and the observations. That is very clear in the content, in the absorption or the scattering ratio, and also in the fluxes that we are deriving in terms of the forcing. Now, to facilitate a comparison, we have now drawn the regional means and the biases that occur because of the differences with respect to the Aeronet and the model simulations, namely the CMIP6. The regions I have highlighted or I have shown for ease here. What we are seeing is the bias in the AOD, bias in the SSA, top of the atmosphere forcing, surface, and in the atmosphere. So these are in black is the multi-model mean from the CMIP6 simulation, and the rest of the 6 models, individual models that we used that are part of the CMIP6 project are also shown. So at the outset, we see large differences in the aerosol optical depth. We see that one of the models produces a larger optical depth always, like the Canada Earth System model, while most of the models underestimate. And over the North America, South America, Europe, etc., the aerosol optic, the biases are very, very small. Contrast this with signal scattering albedo, the biases differ, the range is different between optical depth and the signal scattering albedo. Please note this point. And in contrast to the AOD, which is overestimating, the CAN ASM5 actually underestimates signal scattering albedo or overestimates when you compare with the AOD. Now, when we translate these variations into the biases on the surface radiative forcing, we see that almost all the models, the biases are more or less the same. Now, that occurs because of either the small changes in the optical depth that we see or the resultant changes in the signal scattering albedo, because the radiative effects are linear with respect to the change in AOD, while they are not linear with respect to changes in signal scattering albedo. And also, one more thing that was not included in the presentation was that while we looked at previously the differences between the aerosol optical depth, those were derived at one wavelength in at 0.55 micrometer. When we look at the angstrom exponent, which is the spectral distribution of the aerosol optical depth in the range between 0.4 to 1 micrometer, many models, the spectral distribution simulation is very difficult and challenging because it means that they have to clearly bifurcate more robustly the fine, meaning particles that are smaller than 1 micrometer in size, in radius, and the Coarse-Mode particles which are greater than 1 micrometer, which determine the ratio of aerosol optical depths at different wavelengths, and then the aerosol angstrom exponent changes. So it has required, having examined the observations, models, and also the GCAS requirement from the GCAS community, then let us look at the requirements and the challenges that we have. Now, what is clear is that from the ground-based and space-borne, there are both merits and demerits. Ground-based measurements are very extensive and intensive campaigns are very limited, but spatial and temporal coverage is a problem, as we can see from the previous few figures. Satellite measurements, no doubt, they provide global coverage, but we know that they lack in accuracy and resolution. They can retrieve only a select few aerosol characteristics, for example, deriving absorption AOD as a result of single scattering albedo is very, very challenging. So in order for us to get a complete picture, we need to augment the ground-based and the satellite measurements along with global aerosol models in order to address the issues that we faced in comparing the observations and the simulations. So aerosol models, on the other hand, which are developed on the basis of microphysical processes, formation and removal of aerosol species, they need to be evaluated with this full range of observations, physical and chemical. Some attempt we have made in the next few slides, which I will show, wherein it comes as a part of the challenge that we face. So first challenge is, now, can we bifurcate with a clear distinction the natural sources and the anthropogenic sources? First, when you look at the total source, in terms of teragrams of emissions per year, the mass loading and the optical depth in the mid visible, and the species that we talked about earlier, we see that we can there is no direct relation at the outset between the source, mass loading, and the aerosol optical depth. And in general, dust and sea salt is categorized or classified as natural. However, proportion of dust could be anthropogenic. Sulfate, black carbon, and anthropogenic, the organic carbon or the organic matter, is termed anthropogenic. However, sulfate that is emitted from dimethyl sulfide from the oceans and also from the vegetation, which is essentially secondary organic aerosols, be anthropogenic. So this general description or categorization of these two becoming are natural while the other three are anthropogenic is not very reliable. So an accurate estimate of natural versus anthropogenic fraction of aerosols is difficult. Now, the AOD, because it is the total column content that is retrieved from satellites, is more reliable than SSA and the absorption AOD, because SSA and AOD depend on how efficiently we are able to bifurcate the AOD into scattering and absorbing components. And this fact was highlighted for the relation between SSA and the AOD. AOD is the total column content, and we saw the range, while SSA also the range is different. So the relation between AOD and SSA can be contrasting or distinctive. It is generally not seen that regions with lower AOD will have lower SSA or higher SSA or vice versa. That is why I term this relation between AOD and SSA be contrasting and distinctive. Why? Because AOD can change depending on the aerosol column content. When it is more, the AOD is higher. When it is less, the AOD will be lower. But the change in AOD need not change the SSA, as so far we have seen. SSA is the ratio of aerosol scattering to extinction. And this was also seen very clearly in just after COVID lockdown scenario, where the aerosol optical depth across the globe, most of the regions, they decreased by about 20 to 40%. Statistically significant, the single scattering albedo changed only by 4% across the globe. That is because of this reason and this distinct relationship. Now, when it comes to the next challenge, when we come to observations, we have the aerosol optical depth and the single scattering albedo. That measurements are available at different wavelengths. So the spectral variation of the aerosol optical depth and the single scattering albedo of the different aerosol types, these come with a range of values that we are familiar with. So an angstrom exponent of a value that is less than 0.6 indicates dust type particles, which is also aided by the single scattering albedo. We know the range exactly. And then mixed type of species where you have fine mixed versus coarse mixed particles, urban industrial plus biomass burning contributing, leading to higher angstrom exponent and single scattering albedo that is more or less around between 0.8 and lower, depending on what is the emission source, whether it is biomass burning or the urban industrial, and then leading to variations in the single scattering albedo. However, please note that their angstrom exponent is always higher than 1%. Now, contrast this with the outputs that we get from the model. Now that we are getting the species contribution or the species AODs. So we have sulfate, black carbon, organic carbon, dust, and sea salt. On the one hand, we know from the observations we have the type. On the other hand, from the model we have the species. So one of the things that we need to emphasize is this handshake that should happen between the observations and the models in terms of identifying the source regions, the types of particles that are produced, and then trying to constrain this in the modeling scenario so that we can find out the reasons for the discrepancy between the characteristics in terms of source regions, the emissions, and how the dispersion of these particles to other regions are occurring. Now, I mentioned that it is very difficult to measure the absorption aerosol optical depth. That is because the absorption AOD is actually about only 20% of the AOD that we are measuring. Remaining 80% is scattering AOD. It's identical to looking for a needle in a haystack. And this light absorption by aerosols, it determines the atmospheric heating. So the current climate models, the state-of-the-art representation of physical and chemical process, they grossly underestimate the aerosol absorption in many regions, especially over Asia. This was borne out by the CMIP6 simulations as well, almost in all the models, and over the region, which is a aerosol hotspot. Now, when we compare and contrast the aerosol optical depth and the absorption AOD, we see that there is clearly a significant difference in the range. The absorption AOD, as was pointed out earlier, is only about 20% of the total AOD. Most in many locations, it is even lower or higher. The optical depth is lower, and the absorption AOD is also lower, leading to higher single scattering albedo. The spectral single scattering albedo, spectral nature of single scattering albedo also varies as a function of region and as a function of season, depending on which type of particle is dominating the atmosphere. Typically, in an urban environment, the single scattering albedo will decline as a function of the wavelength, as we see over North America and South Asia, for example. But in regions where it is dominated by dust, as we see in North Africa, we see that the single scattering albedo increases as a function of wavelength. Similar variations as a function of season and region are seen shown here. The very purpose with which this investigation began, looking at the seasonal variation in the aerosol optical depth and the single scattering albedo and the associated aerosol radiative effects, clearly show, for example, the seasonal variations are significantly higher, larger, or significant statistically when compared to the interannual variations. And this also helped us in determining, for example, that the regional variations, we see that all the 4 seasons, the North America, Europe, etc., the single scattering albedo and the optical depth, then as a function of wavelength, shows very minimal differences, clearly emphasizing the fact that the content and the composition over these regions throughout the year are more or less the same. Now, one of the other challenges is that how these aerosols are mixed in the atmosphere. They can remain in the atmosphere as externally mixed, meaning there is no physical or chemical interaction among these different type of particles that are present in the atmosphere, such as black carbon, sea salt, sulfate, dust, etc. Or they can remain in a core shell or a homogeneously mixed in scenario. For example, in core shell, one species forming the core and the shell is of a different species, such as mineral dust, the illustrations of which are shown here, could even be fractionally mixed. For example, on the surface, it could be about 15 to 30% of black carbon on the mineral dust species. While the other contrasting scenario is where all these are homogeneously or internally mixed, where you get one single entity. Whatever be the species, everything is internally mixed, all physical and chemical interactions taking place. So we get one homogeneous entity of the aerosol, and which will change the single scattering albedo and also the aerosol optical. So it comes to the point where and why this mixing is making a change. When we analyzed the aeronet aerosol absorption across different regions, including Asia, we find the aerosol absorption in the aeronet simulation or retrieval is internally mixed aerosols. And when model simulations were conducted by Kelasidas et al., and they simulated the aerosol absorption with proper representation of BC morphology and this mixing that I pointed out, then they found that the absorption that is simulated by the model is close to what is shown or retrieved from the observations, clearly indicating that aerosol mixing state will play a major role in constraining the fluxes of the radiative forces. Then, to conclude, in summary, so we began with aerosols, the sources, the characteristics, how they change. We also looked at which is natural and anthropogenic species. We looked at the radiative effects and how they impact the climate. In terms of the challenges that we face, both in terms of observations and model simulations. One of the major challenges is to disentangle the natural from the anthropogenic sources, and also distinguish the fine versus the coarse, because we need to retrieve the spectral variation of the aerosol optical depth and the single scattering window from model simulations. Meteorology, for example, hygroscopic growth, because of the changes in relative humidity, can change the particle type, AMOD, and the signal scattering albedo, and the winds, for example, can transport this aerosols that are produced from one region to the other. We need to account for that, and then the differences or the challenges in kind of doing a handshake between the species that we get from the model with respect to the types, that is from the observations, so we can identify or reduce the errors in attributing these challenges to aerosol sources or the regions from where they are produced. Hence, also constrain the emission inventories and improve the emission inventories. Once again, thank you for your time, and I'm happy to answer any questions.
Thank you. Thank you so much, Professor Ramachandran. It was really very informative talk. And as it will be available on our YouTube channel, I'm sure many students are going to use it for their understanding. So now it's the time for question and answer. So what I request audience to raise their hand, and I will call them one by one. There are some questions in the chat box. If those people who have written in the chat, if they want to ask directly, they can ask. Otherwise, I will read it out afterwards. So first, if somebody wants to ask directly. Yes, please.
Hello.
Yes, Mr. Devara. Yeah.
Yes. So first of all, I appreciate the well-experienced talk, and then it is an excellent and then highly insightful talk. There is no doubt about it. But I don't want to ask very general questions. I have one clarification required from Dr. Ramachandran.
Okay.
That is, we talk about black carbon very much nowadays.
Correct.
Forget about all other types of aerosols. But as we know, carbonaceous aerosols, basically they have two types. One is organic, other one is black carbon. Of course, people talk black carbon and elemental carbon, one and same, but they are not like that. They are different. We know that. But you also talked about black carbon and organic carbon.
Yes.
I wanted to know from you, because you are one of the persons in India, those who have done global analysis, not regional. So, is there any region where organic carbon compensates the black carbon, or black carbon compensates the organic carbon? Is there any?
Is there any region you said?
Yeah. Region or location or whatever.
Okay.
In smaller scale location, or you consider a little bit bigger.
Okay.
Is there any region?
Okay.
Because location is very difficult to answer. I wanted to integrate it to some particular scale, regional scale.
Okay. I will let me go back to the presentation.
See, my point is there any region where organic carbon compensates the black carbon, or vice versa?
Well, here is you can see the figure, no?
Yeah.
Species, yeah. So the organic carbon, which is on the right corner, for example, there is no compensation that is evident, right? For example, if we concentrate in this region, please note that first of all, the percentage contribution of black carbon to the total is about a factor of 4 or 5 lower than organic carbon and black carbon. But this is compensated by its radiative effect. The single scattering albedo of black carbon is at least more than 4 times higher than that of single scattering albedo of organic carbon.
Agreed.
So, and here also you see these regions where you will have sulfate and also vegetation, etc., you will have more of organic carbon, while the other regions it will be less. Black carbon is visible over regions where there is a lot of fossil fuel and biomass combustion, as can be seen from the hotspots. So there is no net effect. Organic carbon is still, if you look at the radiative effect, both of them, black and the organic carbon, the radiative effect is still very highly uncertain across the globe.
If I can add to the question, I think he's talking about the brown carbon, which is similar to black carbon in absorbing, but by nature it is organic carbon.
Yeah. I mentioned that. Yeah, I mean, I was talking about the what he was asking, where is there a compensation that is occurring? So
You see,
the point is,
there must be some regions where you can have the scattering effect and then absorbing effects are more or less same. Is there any reason you found so far?
No. Here, that's why I was, for example, if you point out, if you look at it here, the contribution of organic carbon in this region, which is South Africa.
Africa.
So if you look at it, for example, if you take this is 50%, while this is only 10% black carbon. Organic carbon is 50%. This is about 10%. Now, if you look at the radiative effect, so this is the, if you look at the optical there will not be any change because this is only an addition. If you look at the radiative effect, this radiative effect due to this percentage of black carbon will be same as that of the organic carbon because of the single scattering albedo in these species, variations.
Okay. So in radiative forcing calculation, what is the parameter which is compensating as compared to AOD?
The single scattering albedo. Yes.
SSA is compensating.
Yeah, because it is non-linear. No. Yeah.
Okay, that's good piece of information for me. Thank you. Thank you, Dr. Ramachandran.
Thank you, Dr. Vivara. Yeah.
Okay. Dr. Abid Kumar, I can see your hand raised.
Yes, sir. Actually, in slide number 6, there is a insoluble aerosol particle are higher size or mode rather than the soluble particle. So what might be the reason why this median size are the mode of the this slide? Why this insoluble particle has the higher mode or a higher median diameter than the insoluble one? What is the maybe reason?
When you say insoluble, these are mostly soil and organic material consisting of, that is typically in urban region, the suspended road dust, etc. So these are typically larger size particles. No? Only the mode radius is higher, but look at the number. This is less than 1 as compared to the fine mode particles, which are more than 10,000.
Okay.
Okay, so now let me read out some questions which are in the chat box. First question was written by Ramachandran Ghosh. And he asked, does localized pollution cause more cloud formation and convection?
Localized oh yes, there have been studies which indicate that, but it also depends on which species, which is dominating, etc. So it's not a very clear or a straight cut answer that we can. There's a lot of uncertainty.
Okay. Other question is by Dr. Srinivas Rekha from MOES. He has two questions. First is there any instrument to measure the semi-direct effect that is happening in the clouds? And second question is it possible to quantify how much semi-direct and indirect effect in clouds with respect to the regions, season, etc.?
Okay, this is coming from MOES. I'm sure I will have to touch upon Kai Peaks. I'm sure he knows about that experiment. We can document the semi-direct effect by measuring the cloud droplet nuclear concentration, aerosol properties, etc. within the cloud and all that. But it comes with a large uncertainty. First thing. The second thing is that even now the semi-direct effect and the indirect aerosol radiative effect, they show the largest uncertainty, which is on the order of about 100%. So the answer is that it is very difficult because of the uncertainty that is involved in the growth of aerosol, in how they vary as a function of size, what is the number, what is the density, when they will rain, when they will precipitate, etc. So that is a large uncertainty, and research, I'm sure, as you are aware, is going on across the globe on this aspect. Yes.
Dheeraj sir, you unmute yourself, then you.
Sorry. I muted myself. Sorry. Okay, so next question is by Vignesh Sarangi. And he asked, are there established methods or observational constraints that enable the evaluation of radiative forcing at the surface or within specific atmospheric layers?
Yeah, there are observational constraints. Yes. There are methods that are available. Yes.
Okay. And the next question is Rudnil Singaroy. He is asking, does aerosol affect more cloud formation and convection? If does, how?
Yes. What is that? Can you please repeat the question?
Aerosol affect more cloud formation and convection? If so, how?
Well, aerosols can serve as cloud condensation nuclei for sure, but convection is dependent on other surrounding parameters. So it depends on the moisture, the temperature, etc.
Okay. And another question is by a student from Delhi University, Swati Joshi. And she is asking, how does the inclusion of brown carbon as individual species affect regional climate projections in high emission regions like South Asia?
There is a large uncertainty as far as the black carbon emissions are concerned. But the absorption of black carbon, since it is significantly higher, any small uncertainty would actually lead to a larger uncertainty in the future. And the scenarios do have some uncertainty related to black carbon, as is clear from this this you can see that the black carbon uncertainty is higher. It can go both ways.
Okay, so it seems now there are no more questions. So let us come to the last part of the talk, which is vote of the thanks. So for that, first of all, I would like to thank today's speaker, Sir S. Ramachandran, for kindly agreeing to give this talk. Thank you so much, Mr. Ramachandran. And then we will thank the team, BRC team, who is doing all the work behind the scenes to arrange the lecture. So thank you, BRC team. And most importantly, the audience, which is here always to listen to our speakers. So thank you very, very much for joining the lectures and interacting with the speakers. And with this, I would like to stop. I see there are two more questions, but I don't know. Do you want me to read that? You are muted, Professor Ramachandran. You are muted. Professor Ramachandran?
Okay.
Yes.
Am I audible?
Yeah.
Oh.
So can I take the person has written? So let me read that. Yeah. Dr. Avinash Kumar Ranjan. As we observed that Moody's AOD is overestimated compared to Aeronet, so can we use any factor to reduce the bias? You are muted, Professor Ramachandran. You are not audible. You are not audible.
No. Now you can answer.
Are you audible now?
Yes, now you are. Yeah.
Satellite diffusion of AMOD parameters surface albedo. So the retrieval algorithm takes into account several of these: solar rate angle. Two single factor can. So our effort, for example, aeronate or assess. We made sure that we did what we call as the space time.
For the vector,
Plus or minus 25 kilometers. Right? Plus or minus 30. So it's all will play a role straining the satellite retrieval. Evaluating the biases that satellite.
Okay, Miss, I think there was some issue with the Miss,
audio.
the audio. But anyway, thank you. Miss, I think we should stop now. So thank you once again.
Thank you, Dr. Ram. Thank you very
Thank you
much.
very much. Thank you.
Okay.
Thank you.
So we'll stop now.